So, hi, I'm Dipan Pal. I'm from CMU Sala Biometric Center, and I'm here to present our work on discriminative invariant kernel features, which was done in collaboration with Juefei-Xu and Mari Savides. So, discriminative invariant kernel features is basically a general feature extraction method, which can be used for a lot of our pretty large class of vision problems. But for this paper, we focus on face recognition and pose estimation. So, who is the subject and what is he, where is he looking at, pretty much. So these two are complementary tasks, but we try to do them simultaneously using a single unsupervised feature extractor. The paper focuses on dense landmark-free approach, so we only use two eye center locations, as shown or illustrated in the figure on the bottom right. But we can also extend this to a completely landmark-free approach, which is also alignment-free. So in that case, your input would be just an image with the face covering most of the image itself. We extract a single, highly discriminative, non-linear feature from raw pixels for both tasks. This is the common feature for both tasks, and this is provably group invariant. And in fact, that is also our approach to this problem, that we want to be invariant to Newton transformations. We basically model all these groups as unitary groups, so we are explicitly invariant to translation and rotation. But we also hypothesize that we can be invariant to groups such as which incorporate pose variation. So for example, if you have two faces here which are multitude of poses, we would want to ideally have a feature which basically is invariant to pose and maps all of these points to a single point. And hence, the learning complexity or sample complexity is reduced. So previous work, which is actually the work of Tommaso Poggi at MIT, sorry we don't have the citation here, it is in the paper and on the poster. They build linear invariant features that are implicitly discriminative. But invariance theory in a nutshell that they propose here, in a few sentences as follows. When a group of transformations act on any image, they create an orbit, which is a set of transformed templates. Now, this orbit itself is unique to the object, and it is in itself invariant to the transformation group. Hence, any function or any measure of this orbit is itself an invariant, implicitly discriminative feature. But to characterize the orbit, previous work simply used sample templates, which is basic. For example, for face recognition, they would just use faces. But we find that, not surprisingly, explicit discrimination provides better matching. So moreover, we have that the learned templates also form a group, and hence group invariance theory does hold. We also find that we can do this in the kernel space, and this is a main theoretical contribution. We show that discriminative non-linear templates also form a group in the RKHS, and which leads to the method of discriminative invariant kernel features. So our final practical system is pretty versatile. We can do face recognition and pose estimation with the same framework. For the face recognition sub-feature, it just pools over pose variation and vice versa for the pose estimation. This is just a feature extractor, so you can build a classifier on top of this. For all experiments, our classifier is basically a cosine distance. So for just a few results from two of our experiments, we have a pretty large semi-synthetic data set. Semi-synthetic because it's kind of rendered from a 3D model with real texture. And we compare the kernel features to the baselines of sample templates, which normalize dot product, and the linear corresponding method. So not surprisingly, max-pooled DIKF does work the best, but more interestingly, it also matches the state of the art on 2 FTP protocols, despite being much simpler than competing methods and working purely on raw pixels. So this is the same model that we use across most of our face recognition experiments. So thank you so much, and please find us at post number 32 for more details.